Our universe is a place of constant motion. From the smallest particles to the largest galaxies, everything is in a perpetual state of flux. One of the most profound discoveries of the 20th century was that our universe is not static, but rather it is expanding. This means that the very fabric of space is stretching, carrying galaxies along for the ride. Imagine a balloon with dots drawn on its surface. Each dot represents a galaxy. As you inflate the balloon, the dots move farther apart, just like the galaxies in our expanding universe. The expansion of the universe is not like an explosion, where galaxies are flung outwards from a central point. Instead, space itself is stretching, increasing the distances between galaxies over time. This expansion was first observed in the 1920s by astronomer Edwin Hubble, who noticed that light from distant galaxies was stretched, making it appear redder than expected. This phenomenon, known as redshift, is similar to the Doppler effect we experience with sound waves. Just as the pitch of a siren drops as it moves away from us, the light from distant galaxies is stretched, shifting towards the red end of the spectrum as they move away from us. The discovery of the expanding universe revolutionized our understanding of the cosmos and raised profound questions about its origin, evolution, and ultimate fate. What is driving this expansion? Will it continue forever? Or will the universe eventually collapse back in on itself? These are some of the biggest questions in modern cosmology, and they continue to fascinate and inspire scientists today. The expansion of the universe has a profound effect on the distribution of galaxies. As space stretches, the distances between galaxies increase, causing them to drift apart like ships passing in the night. This effect is most pronounced for galaxies that are already far apart. Imagine two galaxies separated by a vast expanse of space. As the universe expands, the space between them stretches, increasing the distance between them. The farther apart the galaxies are, the more space there is to stretch, and the faster they will appear to move away from each other. This relationship between distance and speed is known as Hubble's law, and it is one of the cornerstones of modern cosmology. By measuring the redshift of a galaxy, astronomers can determine its speed, and in turn, its distance from Earth. This has allowed us to create detailed maps of the large-scale structure of the universe and to study the distribution of galaxies over billions of years. The expansion of the universe also has implications for the future of galaxy clusters. While gravity holds individual galaxies together in clusters, the overall expansion of space means that clusters are becoming more diffuse over time. In the distant future, it is thought that galaxy clusters will become increasingly isolated, like islands in an ever-expanding cosmic sea. To understand the expansion of the universe, we need to shift our perspective from thinking about galaxies moving through space to thinking about space itself expanding. This is a difficult concept to grasp because we are used to thinking about space as a fixed and unchanging background, like the stage on which the cosmic drama unfolds. However, Einstein's theory of general relativity tells us that space and time are not absolute, but are interwoven into a dynamic fabric called spacetime. This fabric can be warped and curved by the presence of mass and energy, and it is this warping that we experience as gravity. The expansion of the universe is not caused by galaxies moving through space, but rather by space itself stretching, like the surface of a balloon being inflated. This stretching is thought to be driven by a mysterious force called dark energy, which makes up about 70% of the total energy density of the universe. Dark energy is a hypothetical form of energy that is thought to be evenly distributed throughout space, exerting a negative pressure that causes space to expand at an accelerating rate. The exact nature of dark energy is one of the biggest mysteries in modern physics, and scientists are working hard to understand its properties and its role in the evolution of the universe. The fate of the universe is intimately intertwined with the nature of dark energy. If dark energy continues to dominate the expansion of the universe as it is doing now, then the universe will continue to expand forever, growing colder and darker with time. Galaxies will become increasingly isolated as the space between them stretches, and eventually even the stars within those galaxies will burn out, leaving the universe a vast and empty expanse. This scenario is known as the Big Freeze. In this future, the universe would become increasingly homogeneous and dominated by dark energy. Temperature differences would eventually even out across the cosmos, leaving no possibility for stars to form or for any complex structures to exist. However, if the strength of dark energy were to change over time, or if there are other unknown factors at play, then the fate of the universe could be very different. Some theories suggest that the expansion of the universe could slow down and eventually reverse, leading to a big crunch where everything collapses back in on itself. Others propose that the universe could rip itself apart in a big rip, where the expansion becomes so rapid that it overcomes the force of gravity, shredding galaxies and even atoms themselves.